Okay. So in this, there is a analog to digital conversion. Analog to digital conversion. So for that, go for some blocks in the analog to digital conversion. The first block is sampler. Sampler. Then go for quantizer. Quantizer. Then go for encoder. So now here it is. The sampler input should be the M of the signal. M of the signal. Sampler signal is M of the signal. So where the M of the signal is the analog signal. M of the signal is an analog signal. The time axis. And it is an amplitude axis. Amplitude axis. What are the signal? Signal should be a sinusoidal signal. An analog signal. So the analog signal, that is M of the signal, the time axis it should be a continuous in time, and amplitude axis also continuous. Amplitude axis also continuous. Both are continuous time. That is amplitude and time axis. So amplitude axis should be a continuous. Continuous. And time axis also a continuous. Both are continuous. Time axis and amplitude axis both are continuous. That is known as analog signal. That is known as analog signal. Can represent the signal is M of the signal. So then the M of the signal is given to sampler. The sampler output should be a signal M of n ts. M of n ts. M of n ts. Now, after sampling, M of the signal can be converted to M of n ts. There is n is an integer value. That should be 0, 1, 2, 3, so on. At 0, what is a continuous. Amplitude will be continuous. So now here it is. The samples are given. This first sample, second sample, third sample. Sample signal, discrete sample signal. This is discrete sample signal is sampled at first sample, second sample, third sample, fourth sample. Like so, whereas in the previous class, this is known as continuous in time. It is a sample, continuous in time axis. Sorry, continuous in amplitude axis. Continuous in amplitude axis. Continuous in amplitude axis. Discrete in the time axis. Continuous in amplitude axis, discrete in the time axis. So what it means, suppose this is one of the sample. Another sample. It has the signal is continuously varying. Signal is continuously varying. So it appeared at the first, that is the one, the first n is equal to 1. N is equal to 1, that appears like this. So at the top of the sample should be a continuous. Top of the sample should be a continuous in what the amount of signal have. What the amount of signal have, the signal should be a continuous. Signal should be continuous. Now, amount of NTS we call as a sampled signal. So sampled at time instance of TS. Sampled at time instance of TS. Now, the sample time instance may called as the TS, sampling time, less than or equal to 1 by 2 FM. 1 by 2 FM. This is the sampling time instance called as sampling theorem. Or also it is called as FS, sampling frequency, greater than or equal to 2 FM, greater than or equal to 2 FM. So this is the sampling frequency. This is the sampling frequency. This may be called as sampling theorem. This may be called as sampling theorem. So already previous class you see that. So when the Fs greater than 2 FM, what happens is there is samples occurred between there is sample, first sample, and the second sample, like this, no? So this is nothing but a guard band between the when you can apply Fourier series expression, there should be a coefficients. That is the C0, the first coefficient, C1, second coefficient, like this. This is the spectral components. These are the spectral components. C0 is the first spectral component, and C2 is the second spectral component. C1 is the second spectral component. So the spectral components between there is a guard band. Guard band. Guard band. When we provide the guard band is provided for this relation only. TS less than or equal to 1 by 2 FM or FS greater than 2 FM condition, there should be a guard bands are provided. So this is nothing but sampling theorem. Sampling theorem. In the sampling theorem, you should be provide the space between the two successive samples. Two successive samples, there should be a space that is not the guard band. So now the greater condition message, Fs greater than now. So how much greater is this? So now the guard band used to protect the signal. Guard band is used to protect the signal. Guard band is used to protect the signal. So this is the sampling theorem. This is the sampling theorem. So if suppose Fs less than 2 FM condition, Fs less than 2 FM condition, what happens it is? Fs less than 2 FM condition, what happens it is? The Fs less than condition, the signal going to be like this. First sample and the second sample. So there is overlapping is occurred. Overlapping is occurred. So this overlapping approach we call as aliasing effect. Overlapping approach we call as aliasing effect. So in the aliasing effect, signal may not be recovered exactly. Signal may not be recovered exactly. There should be some lapse of there should be some signal uh, signal going to be overlap and you may not be recollect. You may not be recollect the exact signal. So at these two conditions, Fs greater than 2fm condition, Fs less than 2fm condition, Fs greater than 2fm condition may called as sampling theorem. At this condition, you are able to reconcile the signal from the samples. Can be able to reconcile the signal from the samples. Whereas at this Fs less than 2fm condition, you may not recollect the signal from the samples. That's why this is undersampling is Fs greater than 2fm or sampling Fs less than 2fm condition. Okay. So now another condition is there. Fs is equal to 2f. Fs is equal to 2fm condition. So this condition we called as Nyquist rate. Nyquist rate. So Nyquist rate may also called as minimum sampling rate. Nyquist rate also may called as minimum sampling rate. So now at this Nyquist rate also can recollect the signal from the samples. What is the recollected signal? Amount of the signal is recollected. So what you are going to do is from the samples, you have to recollect the amount of the signal. From the samples, you have to recollect the okay, students. So if it is Fs is equal to F condition is nothing but Nyquist rate. Nyquist rate is nothing but minimum sampling rate. Nyquist rate is nothing but the minimum sampling rate. So Fs is equal to F condition, we are able to reconcile the signal MRT from the samples, and also Fs greater than 2fm condition also recollect the MRT signal from the samples. ఈ రెండు కండిషన్ లో MRT signal recollect చేయొచ్చు. Fs is equal to Fm condition, Fs greater than 2fm condition. So recollection process is done at receiving end. Process is done at receiving end. So you have to take MRT signal that is sampled and given to quantizer. The quantizer output is encoder output is digital signal. Encoder output is digital signal. So when the receiving end, what happens? It is reverse operation. The decoder and quantizer and desampling. That is the receiving end. At the desampling, what happens? It is you have to convert samples to amount signal. Convert samples to amount signal. That is the receiving. At that condition, you are able to reconcile the amount signal or not based on the sampling here. So at Fs is equal to Fm condition is nothing but the minimum sampling rate, or this is nothing but the Nyquist rate. At this condition, you are able to reconstruct the signal MRT, provided that you have to design low pass filter in ideal case. Provided that you have to design low pass filter in ideal case. So ideal low pass filter design is practically possible. Not practically possible. That's why you can go for FS greater than 2 condition. అంటే మనం MRT సిగ్నల్ రికలెక్ట్ చేయాలంటే ఐడియల్ లో పాస్ ఫిల్టర్ ని డిజైన్ చేయాలి. ఐడియల్ లో పాస్ ఫిల్టర్ డిజైన్ చేస్తే MRT సిగ్నల్ రికలెక్ట్ చేయొచ్చు. ఏ కండిషన్ లో FS ఈక్వల్ టు కండిషన్ లో పాసిబుల్ అవుతుంది. సో దట్ ఈస్ ఐడియల్ కేస్. That's why this condition may called as minimum sampling rate. ఈ కండిషన్ మనం మినిమం శాంప్లింగ్ రేట్ అంటాం. సో మినిమం శాంప్లింగ్ రేట్ లో సిగ్నల్ MRTని రికనెక్ట్ చేయొచ్చు, ప్రొవైడెడ్ దట్ ఐడియల్ లో పాస్ ఫిల్టర్ కెన్ డిజైన్. ఐడియల్ లో పాస్ ఫిల్టర్ ని డిజైన్ చేస్తుంది. సో ఐడియల్ లో పాస్ ఫిల్టర్ డిజైన్ చేయడం అనేది కాంప్లెక్స్ టాస్క్ కాబట్టి you can go for second option, that is FS greater than 2 condition. FS greater than 2 condition లో మనం సెకండ్ ఆప్షన్. సెకండ్ ఆప్షన్ లో ఐడియల్ లో పాస్ ఫిల్టర్ కాకుండా ప్రాక్టికల్ లో పాస్ ఫిల్టర్ మనం డిజైన్ చేస్తే కానీ సిగ్నల్ రికరెక్షన్ చేయొచ్చు. ఎందుకు అని అంటే there is a guard band between the signals. That guard band is protect the signal. That's why FS greater than 2 condition is the best option to reconstruct the signal MRT from the samples. So that's why this FS greater than 2 condition may called as sampling theorem. దీన్ని మనం sampling theorem అంటాం. So FS is equal to condition is ideal case. Ideal case means ideal low pass filter డిజైన్ చేస్తే ఆ కండిషన్ లో మనం FS is equal to కండిషన్ యూజ్ చేసుకోవచ్చు. ఆ కండిషన్ FS is equal to కండిషన్ ఏమంటామంటే నైక్విస్ట్ రేట్ అంటాం. సో నైక్విస్ట్ రేట్ is minimum sampling rate. There is no guard bands. ఎక్కడైతే మనం ఎండింగ్ ఆఫ్ ద పల్స్ ఉంటుందో ద సెకండ్ పల్స్ స్టార్టింగ్. ఫస్ట్ పల్స్ ఎండింగ్, సెకండ్ పల్స్ స్టార్టింగ్ and starting like this. And the first sample is there now. Second sample started. So now third sample also started. That means there is no guard bands. This is the minimum sampling rate. This rate we call as Nyquist rate. So the FS greater than 2 condition is sampling theorem. FS is equal to also sampling theorem. That is the ideal sampling theorem, minimum sampling theorem. So that is FS is equal to condition called as Nyquist rate. So FS less than 2 condition is there no oversampling is done here. There is overlapping is occurred. Signal may not be recovered exactly at this condition. That's why you may not prefer this condition. You can go for this FS greater than 2 condition or the minimum sampling rate FS is equal to. Okay. Okay, students. So now just a minute. So when the sampling is done, the signal is converted to M of NTS now, where N is integer value, TS is sampling time. TS is sampling. At this, the signal is continuous in amplitude axis, discrete time axis. Continuous in amplitude axis, discrete time axis is the nature of the signal and nature of the signal after sampling. That is M of NTS. Now, signal is given to just a minute. Now, this signal is given to quantizer. What quantizer do now? Quantizer. When the signal is this, and the time axis is continuous. Sorry, time axis the discrete is m of NTS, m of NTS, and amplitude axis also a discrete. Amplitude axis also discrete. Amplitude axis discrete in time axis, discrete in amplitude axis. The samples are given to encoder. The encoder have to give a logic 0 for the sample is present, or logic 1 is sample option. So 1 or 0, 1 or 0 applied to the these quantized samples. These quantized samples have to given 1 or 0. So here the quantization error is there. The quantization error means, so when you can approximate the signal. So now some sort of error occurs. Some sort of error occurs. So there is a round of value considered the discrete in amplitude axis. Round of value. So what the round of value? Round of value means, if suppose 0.7 can approximate it to 1. 0.8 also can approximate it to 1. 0.9 also approximated to 1. So for all the cases, what 0.7 is present, that is approximated to 1. 0.8 is present, that is also approximated to 1. 0.9 is present, that is approximated to 1. So what is the difference between 1 to 0.7? 0.3. It is not 0.3. So what is the difference between 0.8 and 1? 0.2. So what is the difference between 0.9 and 1? 0.1. So now this is 0.3 is the error. Then you can measure 0.7 and 1. 0.7 into approximately to 1. That is the quantization error. Or 0.8 into 1. That is also 0.2 is the error. This is the error. Okay. So now 0.9 approximately to 1 also. That is 0.1 is an error. So this error may be called as quantization error. This error may be called as quantization error. That means at discrete in the amplitude axis means can consider the round of value. Can consider the round of value for the sample. Round of value for the sample. That is quantization output. So now the quantized signal is encoded as logic 0 and logic 1. Where logic 0, logic 1 is nothing but a digital signal. Is not digital signal. Now, a continuous signal is given, with the digital signal is appear. Digital signal is appear. So in between, these three blocks are very, very important where they convert analog to digital conversion. The first one is sampler, and second one is quantizer. The third one is encoder. So these three signals are these three blocks are essential to convert analog signal to digital signal. So now The digital domain, what is the advantage? Okay. Now, when amount signal is given, that is continuous in time and continuous in amplitude axis, that is amount signal, or called as continuous signal. After sampling, the time axis the discrete, that is amount T is converted amount NTS. Time axis the discrete, that is amplitude axis also continuous. Time axis only the discrete samples are appear, and continuous in amplitude for each sample. After this discrete amplitude and discrete time and continuous amplitude signal, the sample output is given to quantizer. The quantizer signal is time axis the discrete and amplitude axis is considered as a round of value. A round of value may called as it has some errors are occur, that error is called as the quantization error. Okay. So now the quantized output is given to encoder. The encoder encoded the logic 0, logic 1 for the sample outputs or quantized outputs. Okay. So this is the conversion of analog to digital. Conversion of analog to digital. Okay. So students, please go to the material which I sent you, and in the next class we can go for some old question papers, and we have to discuss the important questions. Okay. Thank you, Ananda.